All right, so before we go too far down the rabbit hole, I just want to kind of step back and begin chatting about different ways we can actually go about encoding one of these nice little graphs. So down in front, you're actually going to be given, let's say, a new little graph. The other one had 20 vertices and clearly allowed me not to count things correctly. So I'm going to scale it back a little bit and just look at a graph that has 10 vertices. So they're going to be numbered 0 through 9. And our very first question is then going to be, if you were given this little graph, how would you go about trying to store this thing? What data type would you end up using? So there's a variety of different ways that you could actually do this. And some of the ways that we go about encoding this will actually then depend on what we want to do with it afterwards. If we're simply just asking a question of reachability, we might lean on one technique. If we're going to begin counting the number of paths, we may lean on another technique. If we're going to be trying to optimize some other type of approach or process, we might lean on a different type. So right away, we're going to basically stare at this thing and try to think through how we actually want to store this thing. One of the kind of first easiest ways, which is maybe not the best in terms of actual implementation, is simply going to be record all of the possible vertices in a big old list. So that's going to be a list V for vertices, which are simply going to be those numbers 0 through 9. So the length of V is obviously going to be 10, which is going to keep track of how many vertices or nodes this particular graph has. Once I have my vertices, I can begin chatting about the edges that are going to connect these things. And one possible way to encode those edges is simply going to basically identify the starting point and the ending point of these things. So we would have some edge between 0 and 5, which would then come as this little ordered pair of 0 and 5. We'd also have 0 and 8, so I'd store a 0, 8. I'd have 0, 9, so I'd store a 0, 9. Then I'd go to the next thing. I'd have a 1, 6, so I'd store the 1, 6. I'd have a 2, 5, so I'd store a 2, 5. I got a 2, 6, so I'd store a 2, 6. Obviously, that becomes kind of clunky. It's a lot of stuff we would have to store. It's a little bit of overkill. It also begins to become somewhat awkward once the numbers begin flipping around. So here I was starting with all of the smaller ones. Well, eventually, as I kept on going, I'm going to also then see a 5, 0. So I might get some double counting of things, and that may be less ideal. It might be totally fine if we know that we're going to have a 0, 5 and a 5, 0. If you were to count up everything in this edge set, I would essentially be double counting it, so you just simply have to divide it by 2. So that's one technique on how we want to maybe begin thinking about encoding this. That's kind of nice to write on paper, but it's really, really clunky to actually implement. So a second technique may be to actually store this thing as a big, massive list of lists. Basically, that 0th index of this list is then going to keep track of everything that 0 is adjacent to. So it's going to then keep track of the 5, the 8, and the 9. Basically, what are the neighbors of this particular thing? You can then look at the 1, and we can see that 1 has one neighbor, which is just the node 6. So we're going to have that, just keeping track of the things that 1 is adjacent to, which is simply 6. Then we look over at 2, and we count the things that 2 happen to be adjacent to, which is a 5 and a 6, and so on down the list. This will have the same type of awkward double counting that the previous scenario did as well, is that once I look at what 5 is adjacent to, well, if you store in the 0 and you store in the 2, well, you're somehow double counting those, which again is totally fine. It's just a thing that you have to be aware of when you actually begin to kind of ask questions about what this can actually do. If you're going to begin counting number of paths, you want to make sure that you're not doubling or tripling up on particular things, and that path from 0 to 5 is one nice little thing, depending on which direction you go. Obviously, when we start having directed graphs and directed networks, that will be really important to stress which one we're actually looking at. But for right now, it's just you might double count, and it might be kind of annoying. Another way that we could store this is making use of a dictionary. The dictionary becomes really nice because I can start labeling these things a little bit more interestingly. I don't simply have to label these things 0 through 9, but I could talk about them as being cities or server names or whatever I want to view these things as. I can store them in that capacity. So the dictionary storage version of this thing is essentially identical to that list of lists that I had before, except for we're going to have this dictionary structure. So I'm going to have a 0, and it's going to say, okay, what is 0 adjacent to? And it's going to have a 1, and it's going to say, what is 1 adjacent to? So The dictionary idea here is just like an old school dictionary, which you go look up zero and you see what is the definition of zero. Well, here the definition is then going to be things that zero happens to be adjacent to. So that's one other way. In the next section, we're going to begin chatting about building this notion of adjacency through a giant array. So this adjacency matrix, which is then really going to keep track of things that we are connected to. So we're going to get this big array of zeros and ones. So it's going to be a lot of terms, but it's going to store all of the stuff that we actually want. I'm not chatting about that one here just because we don't need a lean on that in this particular section, but that's going to become focal in the next section. So if you're looking at these ones and you'd be like, I would never store it like any of these ways, I would store this as a big old array, you'd be totally right, but you're one section ahead of us. So we'll get there in a bit. A couple of just terminology things as we jump into this. When I begin looking at a particular node or vertex, I can look at its neighbors or the things that it's happening to be adjacent to, and I could obviously count those things up. 0 is connected to 3 things, so I'm going to say that the degree of that particular node is then 3. 1 is only connected to 1 thing, so the degree of it is then going to be 1. 6 is actually super connected to a whole bunch of stuff, and that idea of being super connected to a whole bunch of stuff would just simply mean that it has a lot of neighbors, or that its degree is quite large. So the number of things that 6 is connected to is 1, 2, 3, 4, 5, 6, 7. So the degree of that thing happens to be 7. So a little bit of some of the terminology. It's hopefully not super duper new or earth shattering, but kind of gives us something to lean on a little bit. And now we're obviously going to jump into actually doing some stuff with these things, and then beginning to look at all of our favorite little searching processes. So doing a breadth first search as well as a depth first, and then seeing really this question of connectivity coming into light. So I'll pause it here and we'll jump back into that.